Hello, students. Welcome to another lecture on classical electrodynamics. And today we have lecture number 24. And today's objective would be that we would like to obtain some expression for the energy stored in the electric field and the magnetic field separately. And later we will combine them to make the expression for the electromagnetic field. So, initial objective would be that we will consider electric field alone and then obtain the energy stored in the region of space, a particular region of space. And similarly, we will repeat the calculation corresponding to the magnetic field. In fact, this particular information, namely the energy stored in a region of space, is required in connection with what we have done in the last class. So, in the previous lecture, which means lecture number 23, we have discussed on the energy transported per unit time in some region of space. Of course, we are going to talk about per unit area later. Okay, for the time being, remember that energy calculation will be done for every second, because if you are going to consider electromagnetic wave propagation, then energy is getting transported from one place to the other every second. Therefore, we have to deal with the calculation per second. And later we will include the concept of energy per unit area. We will also include later, so that energy per unit time, per unit area will be the one what we are going to call by the name Poynting vector. So that was the objective. In fact, in the last class, our objective is to understand what is meant by a Poynting theorem. And for that, we need this information. Okay. We need what information is required is we need to know what is the energy density in a region of space. Energy density means energy per volume. That means if you are going to consider 1 cubic meter of space, in that space how much energy is present. That is known as energy density. If you are going to consider the total energy in all the spaces, then we will say the energy in joules. Anyway, as we go along, these things will be clear. So let us first of all start with the pure electric field, and once we finish that, we will come to the case of the magnetic field. Now, what would be the starting point? Now, how are you going to start the calculation is that energy is generally you know from from your what you call the undergraduate course, that if you want to assemble a system of charges, okay, if you are going to bring 100 charges from somewhere, and that somewhere is what we call infinity. So technically speaking, if you are going to bring one by one from infinity 100 of the charges and then keep at some places, those places is what we say r is the position vector. So r1, r2, r3 will represent the position of the charge 1, charge 2, charge 3, etc. So if you are going to keep 100 of them, that is what is this n here. Okay, the small n is the 100 of them if you are going to keep, then the amount of energy that you are going to spend in assembling that system of charges is given by the product of the charge and the potential that is generated by the remaining charges. Now, how do you know this expression is? This expression is typically derived in undergraduate courses. So in case if you are not or if you want to refresh your memory and then see how it really works like that, then you please verify lecture number 15 in our series of lectures at the BSc level. So remember that we have lecture number 15 for MSc and also lecture number 15 for BSc. Both are there. So make sure that you choose the BSc level electromagnetism lectures and then go to the lecture number 15. We have derived this particular expression which represent the energy required to assemble n number of charges. And in that lecture, I have explained why there is a factor 1 by 2 coming there. And this 1 by 2 is basically coming because of the way in which you are going to count the number of charges. Because n is going to be a large number, counting the number of charges would be a little difficult. So Einstein has given a way to count, and the Einstein's method of counting actually does double the counting. So if you are bringing 100 charges and you are going to count according to the Einstein method, then you will be getting 200 as the count. Now, in order to compensate that, we put a half there, 1 by 2. Okay. So that's the reason for 1 by 2. And anyway, that explanation is there in the lecture number 15. So you can have a kind of refreshment and then return back to this place in this lecture. So once these things are clear, then we are ready to convert this, or we are ready to rewrite this particular equation for continuous charge distribution. Okay, we don't want discrete charges. So we are rather interested in getting the situation for the continuous charge distribution, which means that let us put the integral in instead of the summation. That's what we are going to do. So you put a 1 by 2 and then integration, you put it instead of the summation. And as you can see that the charges will be replaced by charge density and the rest of the thing is same. So you can easily understand how this works. The Q is becoming the integral of the rho. The integral of the charge density over the volume d omega. So d omega represent some region of space, whatever be the region of space that you are going to consider, and then multiply by this V of r. Now as you can see that the index I is not required because it is a continuous integration, and the region of integration will be the entire omega that you are going to consider. So let me therefore write omega, and omega is basically the region of space that you are going to consider. So the question comes, what should be the region? So I would like to write down what is the region to be considered. So the omega should include all region of charge distribution. So wherever you have charge distribution, those regions you will have to cover. Okay. Otherwise, the calculation may not give you the correct value. That's the meaning. That's what I am trying to say. That means, so what is the meaning is, that is the minimum volume that you have to consider is this much. So that is the minimum volume that should be considered. So this point should be clear. Otherwise, you do not know what is this d omega. So as you say, mathematically speaking, it's nice. Omega integral is there, okay, over some region of space. What region of space should be clear? And that kind of clarity will come again. You go back to the previous expression. In your previous expression, if you see I equal to 1 to n, which means that you are considering all the charges that are present in the region of space. So in some region of space only you have kept those n number of charges, right? That entire region of space has to be included. And if you include that volume is the minimum volume that you are considering. Now, why do you want to use the word minimum volume? Is that you can always consider anything larger than that. Okay, suppose if you are going to say that a 10 meter cube is the entire volume in which I am going to keep all the charges, then you need not restrict it to only 10 meter cube of the space. You can go to 100 meter cube or 1000 meter cube space surrounding that. Okay, that should be enclosed inside. That is the meaning. You should not leave that and choose another place. That is the point that I am trying to explain. It is including all the region of the charge distribution. So you first of all consider that particular space where charge distribution is there, and then you can expand the radius of the sphere and then include any bigger volume. And you can ask the question, how can you include all the bigger volume? Is that knowledge you will be getting once you understand what is this electric potential. So the electric potential will be given by how much? If you are going to take a point charge, you have Q divided by 4 pi epsilon naught r, right? That electric potential. So that electric potential will be how long this potential will survive. It will be there for 100 meter, it will be there for 1000 meter, it will be there for 1 kilometer. Even if you go after 1 kilometer, 2 kilometer, etc., you will be having the electric potential. Potential falls down or potential falls off like 1 over r. That's fine. But electric potential will keep on reducing, but the potential will be present even at far away distances. Only if you really go at infinitely large distance, then you say potential is zero. So now you are convinced, or now you have a valid reason why you can always consider the largest possible volume. You can always consider all the large volume so that the electric potential is present everywhere. That is the point to be noted. Okay, but the minimum to be considered is the place where the charge distributions are there. If you are leaving out some charge distribution, then automatically this integral will not give you the correct value. So that's the point, and therefore here is the place where little explanation is required. So that's what I have explained now. and the statement is clear by writing an additional information. Whatever I explained, I am writing here. We can always consider an additional volume so that all the region of space can be considered without any trouble, and we will be getting the required expression for the energy stored in that region of space. So that region of space is very important. Whatever region that you are going to consider, that region of space. So once that this much is clear, now we can start doing some calculation. So let me therefore move down here. And the rest of the calculation involves only the substitution of the Gauss law. So there is a rho there, right? So that we are going to substitute that epsilon naught times divergence of E. Then we have multiplied by the V of R, then into a d omega. So you can easily see how this comes. There is a charge density that is present here, and we would like to rewrite like this. In fact, you can ask the question, why do you want to do this kind of rewriting? Okay, so if you don't have to rewrite really, if you ask the question, if you evaluate this integral, and that's enough. This is the actual expression for the energy stored in a region of space. So actually in one line you got the answer. But however, there is an alternate way of rewriting this kind of equation. What is the way to rewrite? And second question is, why do you want to rewrite? So the answer is now clear. If you see the appearance of this equation, this charge density is we say it is r prime, but if you look at the potential, it is written as a function of r. So what is the difference between r and r prime is, r prime means it is the place where charges are present. R means it is the place charges are not present but electric potential is experienced. So wherever you stand given by this R vector, at those places you will be able to feel the electric potential. That is the meaning. And R prime means if you are going to stand at R prime, then it is the same place where charge is present. So that is the difference between R prime and R. So therefore, this particular d omega should include all possible spaces that you are going to have. But however, there is a technical difficulty. What is the technical difficulty is that if you look back to the very first lecture in our series, MSc level lecture I'm talking about, the very first lecture, we have seen that the application of the Gauss divergence theorem to the electric field, diverges. So you see that there is one lecture called Divergence Diverges. That is the title of the lecture. So what is the point to be noted is that you cannot ask the question what is the electric field at the same point where the charge is present. Okay, that region is already occupied by the charge. So you can't ask what is the electric field or what is the electric potential. And therefore, you should not consider the exact place where the charges are present. That is a singular point. So the singular point I have explained in that lecture, and then the need for the Dirac delta function is also explained in that lecture. Okay, the title of the lecture is Divergence Diverges. So this kind of technical difficulty is there if you are going to deal with R prime and R together in a region of space. So therefore, because of this reason, what happens is it would be better you eliminate this charge density term. Only term you are eliminating. Okay, charges will be there in that place. So we are going to somehow eliminate this charge density term using the Gauss law. Okay, it is exactly the Coulomb's law rewritten. The advantage is that the Gauss law can be rewritten by taking the epsilon naught cross multiplication, and then you get this. So what is the advantage of writing this is, this particular equation does not have any primed variable. You see, R prime is there here. Now there is no more R prime. Electric field is a function of R. Electric potential is a function of R. There are no R primes are there. Therefore, in this way, if you write this kind of the singular points will not enter into picture, and therefore it will be easy for us to proceed with our calculation. And that is the one of the main reason. And the second reason is, of course, this particular equation clearly tells that we are discussing the effect. Effect means potential and electric field are the effects, and then the source or the cause. The cause is the charge density. So in this first expression, so in this expression, you have both the cause and the effect. Cause effect is there. This is the cause. Rho is the cause and V is the effect. So this is a mixture is there. But here, if you rewrite like this, both of them are effect. Okay. So that means you are not going to worry about the reason why the electric field has come. That kind of question is not there in this expression. And we are going to talk about only the effect. Effect means only the electric field and the electric potential. So because of this reason, we are going to rewrite. And once this step is clear, then rest of the thing is very simple. We are going to use some product rule and then rearrange it to terms. And therefore, I would like to write down whatever I explained for the time being. So this is the what I have explained. So we are going to consider only the region where the fields and potentials are present. So without worrying about the charges, that's the meaning that I have written. And once that is clear, let us now simplify this expression using some kind of a product rule. So let us see which product rule is useful. Okay. First of all, let us write down like this. And now this is the almost very important equation. It looks like this. And then let me put a box for this, because we will come back to this equation. So I'll put a box and say that this is the required equation. And then let us identify some terms for the product rule. So you can see that this is the product rule that I am going to use. And there is a divergence of scalar times vector. So we don't have that term directly here. But instead of that, if you see the last term, you don't have it here, isn't it? So the last term also it is not there here. First term is also not there here. But only in this particular term, you have f of r into divergence of A. So that particular term is now visible here. How it is visible? That f of r is the scalar, v of r is a scalar. Divergence of A, divergence of E. Therefore, this particular term corresponds to what we have here. And therefore, this particular product rule can be used. That's the meaning. And that is the reason why we identify f and a. And once this much is clear, let us therefore rewrite this expression. I want to give some equation number for this, and let us integrate the product rule over some volume, because our equation 1 has an integration. So exactly nothing. This is integration in what are you going to integrate? This one. There is a product rule, right? This entire expression, divergence of FA equal to this entire equation, you are going to integrate over this d omega. So you can understand why you are integrating. Why means our expression for the energy has the integration. So the same integration should be present in the product rule also. That is why we are integrating. Okay. So let us therefore integrate over the volume omega divergence of. Now let us substitute and see. F means V, A means E. E is a vector, okay? Then d omega, that will be equal to. So what is the first term? You put the integral over the omega. F means electric voltage, and then you have divergence of electric field. Then you have a d omega, and then you have a plus electric field as a function of r. You have a dot product gradient of the electric potential, and that's all. So which means that we are now substituting the f value and a value. Maybe I will show it once again. See this kind of expression, this f and a we are appropriately substituting here. That is what I have done here. So once this is clear, we have now two terms. There are two terms are there. Which term is present in equation number 1? That you have to identify. So let us identify that the first integral here is the term in the equation number 1. Okay, so this is the one that is required, and hence let us now proceed further. So I will bring this particular term to the left side. So now I will put it in the left side. Integral over omega V of r divergence of electric field d omega. So it has come to the right side. That is equal to, here we can do one thing. I want to write the surface integral actually. So how surface integral comes, let us see. So this particular term has come to the left side. Okay, and then what happens is you can take this to the left hand side and then write with the minus sign. That's fine. Now coming to this term, this has a divergence. So if you apply the Gauss divergence theorem, I can write down the normal component of V here. So therefore, this particular volume integral will become a surface integral. So that is exactly I'm trying to write down. So now the closed surface integral of, now we are going to write down the normal component of the voltage multiplied by, this is voltage multiplied by electric field. Because it is normal component, you have to put a ds here. In fact, I am not explaining more about this. How the divergence is converted to the surface integral, I am not explaining. Because we have been using the Gauss divergence theorem in several of the lectures from the beginning. So you see the first 5 to 6 lectures, uh, our series of lectures in MSc, we have been doing this Gauss divergence theorem several times, and therefore now I don't want to write down all the in between steps. So the volume integral is now converted to the surface integral according to Gauss divergence theorem. So that should be quite comfortable for you now. And once that is clear, this term I am taking to the left hand side and therefore it is minus. And there is one more thing to be noted here. Electric field is written here. What is gradient of V? Okay, you know what is gradient of V. Electric field can be written as gradient of the potential, but there is a minus sign is there for what you call the convention. Electric potential at infinity is 0, right? Because of that reason, we define E to be equal to minus of the gradient of potential. That also we have already seen, and therefore we are going to substitute that electric field. We are going to substitute. Now you see electric field is equal to minus of the gradient of potential. That is the reason why the minus has come here. The remaining things are the same thing. But however, there is a point to be noted that I will write down later. Okay. This you keep it in your memory. I will write a note about this at the end of this calculation. For the time being, let us proceed for the simplification. So equation 1, let us now, we have an epsilon naught by 2, right? So I would like to write that. So I will write down the W equal to epsilon naught by 2 from equation number 1. So W equal to epsilon naught 2 by, the rest of the thing is same. The only thing is epsilon naught by 2 I am multiplying everywhere. Okay. That is equal to, again, epsilon naught by 2, then surface integral. So that's all over. Then plus again epsilon naught by 2, and you have the electric field dot electric field. So I will write it as modulus of E square d omega. Okay, so that looks fine now. And therefore, what I am trying to do is now, I don't have much space right now. So I want to consider this particular integral as I1. So that's what I'm trying to write now. So consider that, see, there are 3 integrals are there, right? There is one here, there is one here, and there is one here. So out of them, let us now pay attention to this surface integral. So the entire surface integral, we will call it by something like I1. I1 means, first integral. This one is the second integral that you have. And the left hand side, whatever is there is W. So there is nothing to worry about left hand side. Left hand side is exactly W. So that's all about it. Right hand side, you have 2 integral. This will be I1. No need to worry about I2. So I want to write like that. So let me therefore write down that this is I1. And therefore this becomes I1. So it is written here. I2 is almost simplified. There is nothing to worry. So I have just copied here. So now I need some explanation for I1. Okay. So how to, we are not going to eliminate, we are not going to evaluate the integral directly, but we are going to see how this can be simplified in a very easy way. So for that purpose, I need to explain with a diagram. So what I will do is I'll go to a different place in the board because I don't have space right now. I'll move on to a different place in the board, and I will explain how to understand this I1. Okay. So now this I1 I have copied here. Okay. So this is the integration that we are interested to evaluate, and the integral tells that this is the closed integral. So we have to have a closed surface. It can be any surface, okay? A rectangular surface, I mean, three-dimensional. So rectangular box kind of surface or a prism like triangular. Whatever with the surface that is possible, anything you can consider. There is no problem at all. And for the because of the symmetry of the electric field, because the electric field will be there, everywhere in the surrounding region like a space sphere, and that is the reason why we are now considering a spherical region. Electric field is 1 over r square is there, but 1 over r square, it will decay in this direction also 1 over r square, in the vertically upward direction also 1 over r square, in the left side direction also 1 over r square. In the same way only electric field decays. Okay, so that is the reason why you are considering the spherical region. If in different directions you have different power laws, and then it will be a complicated one, and then you'll have to use a different kind of a closed surface. So that is the reason why we are first of all having a sphere here. Okay, that's fine. And then second point is, do you want to consider the entire volume of the sphere, or that we have to consider the surface area of the sphere? So what do you understand from this integral I is that this is a ds. So ds means it is supposed to be a double integral, which means that we will be evaluating the integration only on the surface of the sphere. This is very important. The inside of the sphere, that means the entire volume is there, right? That will not come into picture in this integration. So we have to worry about the integration only on the surface of the sphere. Okay. So of course you are unable to see the entire surface because of the you cannot show it on a blackboard, right? Blackboard being 2-dimension. So we can only see like a line here. That's what it is. So if you are going to consider a small portion of the surface, then that is your ds that you are going to have. And what is the very interesting point is that we are going to consider the radius of the sphere to be very large. Infinity is not a number, that's why we say approaching infinity. So you consider as large a sphere as possible. First question is, do we really have a freedom to consider any large sphere as we like? That is the first question. The answer is yes. That is what I have been explaining from the beginning. In the very beginning of today's class, I took some time to explain that we can consider any sphere which is larger than the region where charges are present. This is the point I have explained, and then only we proceed in applying the Gauss law. And therefore, we are going to consider a larger sphere. The second point is that since you are going to consider a large sphere like that, where is your charge distribution present is, it will be present in the middle here. Okay, so you fixed the coordinate system like that. So any charge distribution is will be present only inside this particular near to the center, because it has come very large here. This looks like a point actually. Okay, over that region only the charges are distributed. So this is fine. Then what is this kind of some kind of brightness is there here? So what is that is, the center point is actually the region where the charge density is present, and then the surrounding brightness, little bit of brightness is there, right? That is representing the electric potential surrounding the charge or charge density. It's not a single charge, okay? It's a charge density. So the surrounding region brightness represent the electric potential, because potential is there, and potential will die away like 1 over r. That means the strength of the electric potential will reduce when r increases. So that is why in our diagram I have shown the brightness also comes down. The center point is having highest brightness, and as you come out of away from the charge density, the brightness is reducing, and the meaning is that the strength is reducing. And so therefore, if it is the story, then what happens if you are going to consider an infinitely large sphere is that at the end, that means on the surface of the sphere itself, the brightness is supposed to be zero, which means that the electric potential will be equal to zero when r tends to infinity. So this small r is what is capital R I have written here. So therefore, when small r is actually the capital R, which is the radius of the sphere, and when that tends to infinity, the electric potential is zero. And there is nothing surprising here because you already know the definition of the electric potential. The electric potential is defined in such a way that electric potential is zero at infinity. This is your fundamental definition. And therefore, basically, the same thing we are making use of now. So because of that, because of the freedom that we have in choosing a largest possible sphere, and because of the reason that the electric potential goes to zero at infinity, we are going to make use of these two things in order to evaluate the surface integral. Now you see that in the surface integral, what is the value of the electric potential? So you have to now you have to be clear. Electric potential where? Electric potential on the ds. Remember, on the ds, not the inside. So on the surface of the sphere, the electric potential is now zero. Therefore, this is zero. And similarly, electric field also will go to zero at infinity. Both of them are same, right? Whether it is field or whether it is electric potential, they will go to zero. In fact, electric field will go to zero quickly because of the 1 over r square. So these behaviors are very clear that these things are going to zero on the surface of the sphere. Remember, on the surface of the sphere is very important, not inside somewhere. If you are asking inside somewhere, electric potential may not be zero. So that is the interesting point here in the surface integration. So whatever I explained now, I would like to write down. So electric potential and electric field, how it varies with respect to the R. So V 1 over R, electric field 1 over R square, isn't it? And therefore the product, what will happen to the product? V of R into E of R, 1 over R cube. So that's fine. And what about the surface area of the sphere? So the surface area of the sphere ds will be 4 pi r square. So that means there is a ds here. So ds will be increasing with r square. So remember that the surface area will approach infinity because of r square. So one fellow is going to infinity. The remaining two people are trying to go to zero. So there is a fight between two people. One fellow approaching infinity, and the two people are trying to go to zero. So the question is therefore, who is the winner? Okay. So now the product, now in the equation you have a product, right? So we have to take the product. So two people are pulling to zero, and one fellow is trying to run away to infinity. So if it is the case, who is ultimate winner? That's the question. So let us multiply all the three terms. So if you are going to multiply all the three terms, you have a 1 over r cube, and then the surface area is r square. That goes like 1 over r. So finally this entire product, the entire product will be 1 over r cube and r square is 1 over r. So finally this big 1 over r, which means that when we are going to go far away, ultimately 1 over r goes to zero. Therefore, the winner is the combination of the potential and the electric field. So that means the combination of the electric potential and electric field, they try to approach zero much faster than the way in which the surface area grows to infinity. So that is the actual meaning of this kind of analysis, and therefore we understand that when the capital R goes to infinity, the entire thing goes to zero, and therefore we say that the integral goes to zero. So the conclusion is that the integral goes to zero, and we let us go back to our original place and then substitute that. Okay, so here the place where we are going to substitute is this one, where we have the I1, and therefore we are making 0 here, and then the left out term is only one term is left out, and now you see here very important point, the integral over omega. Instead of saying omega, I have written all space because literally we have considered an infinitely large sphere, and therefore instead of saying simple omega, we said that the integral is performed on the entire sphere, so that the surface integral term has really vanished. Okay, so that is the conclusion. And then there is an important point to be noted here. So the important point here is that we have used the equation electric field equal to negative gradient of potential. And you remember what it is? It is valid only for the static field. For dynamic field, it is not valid. We have seen this in the previous two lectures. I think the title of the lecture was something like potential formulation. So in that lecture on the potential formulation, we have clearly seen that electric field is not equal to minus gradient of V. There is an extra term coming into picture for the dynamic fields. So we are going to make some kind of an assumption for the time being, that let us consider only the static field, in which case we can simplify the expression for the energy to be this much. And this is very important. We are going to use this expression in our calculation in the Poynting theorem. Okay, so this is one part of the this is one part that I would like to keep, and then let us move further. So keep this result, and let us now go back to the second case. So what is the second case? Actually, magnetic field. So energy in magnetic fields. This is the second part. Now the things are quite simple. Let me explain what we are going to do. There is nothing new here. This particular expression is the electrostatic energy only. This is not for magnetic. Okay, this is the equation we started today's class. Charge density multiplied by electric potential. That will be electrostatic energy. Remember the word static. Okay. Now we are going to calculate the energy for the magnetic field using the equation for the electrostatic. Remember, not magnetic. Okay. So how we are going to make such a transition from the electric field to the magnetic field? We are making the transition based on some interesting analogy. The analogy is this: if you want to make a transition from electrostatic to the magnetostatic, then charge density is equivalent to the current density, and then electric potential will be equivalent to magnetic potential. So magnetic potentials we have been seeing in the last 5 classes maybe. Okay, so therefore you know that the curl of the magnetic potential is actually magnetic field. So that's the point. There is a magnetic potential that we are talking about. So therefore this kind of analogy we are going to make use of, and then we can quickly write down what is the expression for the energy given by this integration. If you don't want to make use of this analogy, then you'll have to consider some kind of circuit and an inductor, current through an inductor. Then you have to use something like L into di by dt, etc. Some energy conservation you have to use in some kind of circuit, and then finally you will be arriving at this particular equation. Okay, so that is a point that I would like to say. So we don't have to go through all that. Instead of that, as long as you know that whatever is charge, that will be similar to the current in magnetostatics. Whatever is the electric field, that will become a magnetic field in the case of magnetostatics. So if you know that much clear analogy, we can therefore write down this integral by removing this charge density and put a current density here. Remove this electric potential and bring the magnetic potential here, and the rest of the thing remain identically same. So that's what I am trying to explain and write down. So now I will write down that the integral is now j of r. As usual, there is a prime, of course, so we are going to eliminate. So as usual, now there is the same trouble is there, namely that the source will have a prime, and then the potential or the field doesn't have the prime, and therefore the difficulty is there, having some kind of singular points, and therefore we don't want to have that difficulty. So we now ask the question: can you eliminate this particular current density and then bring some kind of field? Yes, the answer is yes. It is there from the one of the Maxwell's equation. So you have to search which Maxwell equation is having the capital J vector, and that equation is actually curl of the magnetic field. So curl of the magnetic field is given by mu naught into J, which is actually nothing but the Ampere's law valid for magnetostatic situation. Remember the word statics once again. So once this is clear, we are now in a position to remove the capital J vector. So let me eliminate and write that. So now I get del cross B divided by mu naught. And that's all. The remaining things are same. Okay, there is a dot product is missing. So let me explain this. Yeah, so what I was trying to do is del cross B divided by mu naught. Yeah, now the problem comes. What is that problem is? What kind of product is this? This I didn't explain to you. See, when we are making a transition, I have written J vector and then a capital A vector. This A is also a vector quantity. Okay. So that is the confusion came. This is A vector, right? Therefore, this is also A vector. So you have two vector quantities and you didn't tell whether this is a cross product or dot product. So that is why the confusion has come now. And the confusion can be eliminated if you consider the left hand side. Left hand side is actually energy. So since this is energy, it must be a scalar quantity. Therefore, only dot is allowed. So I would put a dot here. So that is the reason why there should be a dot there. The reason is that W is actually a scalar quantity. Okay, if that is clear, that dot product only I want to write here. That is why this trouble has come. So now this dot product I will write down here. You put a dot vector, then I have the capital A vector, which is a function of R. That's all. And now we are in a position to use some kind of product rule. But before that, let me bring it here first of all. 1 by 2 mu naught. Then you have the integral over omega. Then you have a del cross B, same thing. Then you have dot A. Yeah, only thing is I am not writing A of R. So of course you know, right? A is a function of R. B is also a function of R. So you don't have to write every time bracket of R. So that is why I have removed the bracket of R everywhere here. This looks somewhat comfortable. And now you have to search which of the product rules can be used here. So I will now write down which product rule is comfortable first of all and then explain. Yeah, so I think that, yeah, this is fine. So now the product rule that is required is divergence of the cross product. If you are going to consider this product rule, now you have to search which one. There are three terms are there: left hand side and right hand side first term, right hand side second term. Which term is matching with our integration? Can you see whether the left hand side? No, it is not there here. First term, it looks similar, but is it the first term you have to see? It looks very similar to that, but what happens is that either you can consider this particular term or it can be considered this also. So both of them look okay. There is nothing wrong in this, but let us identify that the last term is same as this. So there is a point to be noted why I am saying like that. This product rule is actually valid for any vector A and B. Okay, mathematics book will tell A is a vector and B is another vector. But now also we have A and B. This is something interesting. In electrostatics and electrodynamics also we have A and B, but this A is actually the magnetic vector potential and B is magnetic field. But here A, B is not a potential and field. So that should be taken care. If you are going to take care, then we don't want to compare these two because curl is A here, curl is B here. That is why I don't want this. But here you see, interestingly, curl B is there, here also curl B is there. Dot A vector is there, dot A vector is there. Therefore, the last term really matches with this particular expression. So you don't have to do any mapping. Okay, that is an advantage. And anyway, the minus can be brought and then that can be adjusted. Okay, once that is clear, let us therefore write down the product rule by doing the integration. Okay, so if you integrate the product rule, how it looks like? Integrate means what? Just to put the integral sign, that's all. Will be equal to, so here also you put the integral b dot curl of A d omega, then minus once again integral over omega, the entire expression. So this integral expression is nothing but The same product rule where we have applied the integral, here also integral, here also integral. That's all we have done. So nothing else. And now we are going to bring this expression inside this. Okay, so let us now use the equation number 2. So as I already explained, the equation number 2 is there in the last term. And therefore we can rearrange and then bring it to the left side. Only thing is that you have to take care of the minus sign. So W is equal to 1 over 2 mu naught into. So take care of this minus sign, and then what happens we'll see. So integral over omega, you have the b dot curl of the A vector d omega, then minus divergence of you have A cross B, and that's it, d omega, close bracket. Okay, rearrangement is over. Now interestingly we have one known expression, what is known as the curl of the magnetic potential. So this is something known to you. So if A is representing magnetic potential, curl of the magnetic potential is nothing but magnetic field, isn't it? So that is the definition for the magnetic potential, and therefore let us make use of that. Curl of A equal to magnetic field. So if you are going to use that, then the integral becomes little simple. Integral of omega. Now I get b dot b, right? So what is b dot b? B dot b, I can write it as modulus of b square. And the second thing as usual, I am going to convert to the surface integration. So here I am not going to explain Gauss divergence theorem. Now you might have you are more comfortable in converting the volume integral to the surface integral. So the divergence will be eliminated, and then the remaining term you write it down as a surface integral. That's all about it. So you take the normal component of the A cross B, and that's it. And now once this is clear, we are now in a place to evaluate the second integral. Let us say that this is the integral that we have to evaluate. This integral is the final answer. And now the point that I'm trying to explain is that we are going to the same kind of diagram. I have shown you some kind of sphere, right? We are going back to the same diagram, and then we are going to consider this surface integral. Once again, it is a surface integral, right? So the same sphere is very useful. So I would like to go back to that screen and then explain to you. Okay, keep these points and then let us go back there. The region of integration here, remember, region of integration can be any large volume. That point should be clear to you. Only then you will be able to appreciate the diagram that you have. Any large volume, so as to include all sources. Sources means all the current densities. If it is the case, the surface S in the integration is actually the boundary of the volume. The surface S in the integration is actually the boundary of the volume, omega. So this is something that should be clear to you. Only then you will be able to appreciate the evaluation of the integral. See, you have to be careful in observing something. This is a omega here, there is a omega here. Two omegas are there. The omega, that means the region of space in the integration. The region of space in the second integration are identically same region. When you are converting here, what happened is that this omega is the same omega here, but here you don't have the omega. It got converted to S. So the question comes, what is the connection between S and omega? The answer is that you have the freedom of choosing any larger volume, because this d omega is there, right? There is no restriction that you have to consider only 1 meter sphere. I mean, a sphere of 1 meter diameter. That kind of restriction is not there. For any kind of region that you are going to consider, in that region you will be calculating the energy. That is the ultimate meaning. If you want to consider the smaller region, you will be calculating how much amount of the energy is there in that small region. If you are going to consider a larger region, in that larger region, whatever be the energy, that number will be calculated. So it is not that you will get the same W for all the d omega. Okay, that is a point, very important point. So whichever be the region of the space that you are going to dump here, in that region how much energy is stored, that number will come here for W. So therefore you have the freedom of choosing any large volume, so that we can calculate the energy in that region of space. So this is something that has, even though something looks, certain things look simple, we have to be very careful. Otherwise, you do not know how to connect this omega and s here. So the statement that I have written is, once you decide what is your largest volume that you are interested in, then once you fix that volume, then whatever is the boundary of that volume, that is the s. So this statement, if it is clear, then the same diagram, let me go back to the same diagram and keeping this as the integral I1. Okay, as usual, you consider that as an I1 here, and then we will move on to the diagram where we can explain the other things as usual. So A and B will approach 0 on the surface. That is the reason why we are considering larger sphere. And all other things are very similar. Magnetic field will behave like 1 over r square, and therefore how their product will behave. So the product of the modulus value of A and B will be like 1 over r cube. Okay, and 4 pi r square. Okay, 4 pi r square is what is I am writing r square actually, and therefore what will happen to I1? So I1 will be like integral A cross B dot ds. So the entire product will go like 1 over r. So you know how the 1 over r has come? You're actually multiplying these two. 1 by r cube multiplied by r square. Then 1 by r will come. And then now you take the limit. In the limit of r tends to infinity, the integral goes to 0. So the reasoning and explanation is very similar. But the point to be noted here is that in this integration, all the current sources are there inside, well inside, I mean near to the center of the sphere itself, all the current sources. And because of the current sources, the magnetic field is there in the surrounding region. So you are increasing the size of the region in such a way that the magnetic field really goes to 0 on the surface here. So to that large surface you are going in such a way that B itself goes to 0 on the surface, and consequently A also goes to 0 when you are approaching infinity. The purpose being that the integral ultimately goes to 0. So the idea is, ultimate idea should be clear, that we don't want to evaluate the integral. So without evaluating or without struggling to evaluate the integral, we are now making it 0. Only for that purpose we consider such large, infinitely large region of space, and this is what we are going to call by the name all space. Okay. So we are going to give the name all space. So let me therefore write down this explanation. All the potential or all the field, whatever be the case, everything lies inside. Everything lies inside, and therefore the volume integral takes care of the energy. The volume integral takes care of the energy. Takes care means what? Takes care of the evaluation of the energy. So this statement is important. Let us go back and then see what is the meaning of this taking care of the volume integral. See here, this particular integral is actually the volume integral, right? So because all the sources are well inside the sphere, the volume integral will take care of what is the value inside the volume. Surface integral will take care only whatever is lying on the surface. Since on the surface everything is 0, the integral goes to 0. So that is the idea. If you don't want to consider, well, the important point is this. If you don't want to consider such a large, infinitely large sphere, if you don't want to consider, then excellent. You have to evaluate both the integrals. This integral cannot be done easily. You may have to go to some kind of numerical integration. So this will be a non-zero value. And of course, this also you can evaluate in that region of space. And of course, W will be the energy in that region of volume. It's all fine. Okay, you can consider any other sphere of radius, but remember, in that case, this integral I1 will not be 0. You can evaluate, of course, by a numerical technique, and then if you simplify this entire expression, then W will be given by the energy in that volume. So that volume is very important, not the same volume. Okay. Energy will change when you change the volume. This is very important. If you change the volume, energy will change. That is, W will change. Okay. So keep all these things in mind, and then let us now write down the final expression. The volume integral takes care of all fields. Okay. That's what I have explained till now. And then on the left hand side, if we remember the W, so I would like to write that. So W equal to that much. So remember, once again, I repeat it once again. W depends on omega. If you increase the region of volume, W also maybe, generally it is W is also going to be higher value. If W is very small, if the region of volume is very small, W will be very small. So now what ultimately you have done is this d omega you increase in such a way that it goes to all space. So omega becomes all space. In such a highest volume that is possible, what happens is this W increases, and then it tends to an asymptotic value. Asymptotic value means limiting value, or whatever we say, likely infinite series is converging, right? That's the meaning that you have to understand. When you have an infinite series, it converges to some value, right? That value you will get it for the W. The only reason why we have done that kind of situation is that the second integral goes to zero. Only for that reason we have considered. And because of this consideration, nothing happens to our understanding of the energy, because ultimately we are going to consider energy density. Remember, energy density. Density means energy divided by volume. So at the last minute, we are going to divide it by volume, and therefore, any volume you consider, it's all fine. Energy divided by volume will be same for any kind of volume that you consider. Okay, so energy density is very important, and therefore we don't have to worry about all these things. And finally, total energy, double down. Remember, total energy. So W is the total energy given by the integral over all space. Now I will not write omega, I will write all space. And then you say that modulus of b square into d omega, and that's it. So this is the important expression. So put a box there, and then I want to write a important note about this. What is the important note is that we have used, what did we use? We used del cross b equal to mu naught j in our derivation. So what? So what means it is valid only for the static magnetic field. This is valid only for the static magnetic fields. So this point is something that you'll have to remember, or you'll have to make a note of this, and later we will discuss something on this. So now we are going to almost this is over, and for comparison, I will bring it the previous derivation. For electrostatic field, what is your W? I will copy that now, because both of them are looking very similar. Yeah, so that's the one. So here I have simply copied the expression that we obtained, some 15 minutes back. So the two equations are looking very similar, and comment also looking very similar. What is the comment is that the curl of the magnetic field mu naught j is valid only for the static magnetic field. So that kind of comment is even valid for the static case here, where E equal to minus gradient of V is applicable only for static field. Therefore, the equations that we have derived is generally, or is only valid only for the static electric field and the static magnetic field. So this is something that is to be noted. And another important point to be noted is this is the total energy in the omega volume. Remember, total energy in the omega volume. What is omega volume? Is all space. And therefore, and finally, what we are going to do is we are going to divide this by the volume, total volume that we are going to consider. So W divided by volume is omega. So W divided by volume is known as energy density. And energy density, we are going to use the letter U, that we will see later. W is total energy, U will be energy density. So this is the point that I would like to mention here regarding the comment, and then we are going to make use of this particular expression. And okay, so almost this is final. We are going to use these two equation, and then we will be going back to the Poynting theorem that we will see in the next class. Okay, we will take these two equations and then move ahead to the Poynting theorem, how we can use it in the derivation of the Poynting theorem. That we will see in the next class.